for the last talk. We're having Mattia Rochford, who tell us about like Wilson loop correlators in n equals 4. Super yummy also. Thank you.
Anyway, I just like to. Okay, so thank you very much to the organisers for organising a great meeting and giving me the chance to talk about my work. So I'm going to chat about like Wilson loop correlators in n equals 4 super mills. And this is based on work I've done with my collaborators in Southampton, two who are here, so Rowan and James, and also this is with Omer, who is based in Southampton as well. So just as an overview, I'll give a quick introduction to like Wilson loop correlators, and then extend that to correlation functions of super Wilson loops, where we perform our calculations in twistor space. And then I'll go through some simple examples, so some tree level and one loop correlators. And then with that, those calculational tools, we can then look at properties and simplifications of Wilson loop correlators. So we get an expansion of the correlator in terms of simple integrals called Corel boxes, and the coefficients of these integrals factorize into simple tree level correlators as well, similar to amplitudes. And then I'll talk about the Q-bar equation, which relates loop level objects to integrals over correlators of the lower loop order, and this can often simplify standard loop integration. And then go through a BCFW like recursion relation as well, and some ongoing work. So as I said, we work in n equals 4 super mills, and we work with either both the gauge group SUN and UN. And then the definition of a Wilson loop correlator is simply given as a trace of the path order exponential of the integral of the gauge field over a contour C, where we take that contour C to be a piecewise like contour. As James spoke about in his talk, the expectation value of the Wilson loop can be factorizes into a product of divergences associated to the cusps of the Wilson loop times a finite part times a conformally invariant part. And then we are looking at this correlator weak coupling, so we expand in G squared. So single Wilson loops are well-studied objects because of the duality between scattering amplitudes and Wilson loops, which states that the expectation value of a Wilson loop with n sides is equal to a scattering amplitude of n gluons. And this has led to many developments in scattering amplitudes. So we're interested in correlation functions of multiple Wilson loops, which and they factorize into a similar form to single Wilson loops. So we have a product of the divergences associated to the cusps of each of the Wilson loops of each of the Wilson loops, and then a finite part for each Wilson loop, and a conformally invariant finite piece. So we're interested in these observables for a number of reasons. One is because we believe we should be able to relate them to a correlation function of a Wilson loop and Lagrangian, which is an important observable related to QCD amplitudes. And if we can find a geometric description of Wilson loop correlators, this can help us to understand the geometric description of more general observables in the theory. So the correlator can be separated into a connected and disconnected part. So the connected part comes from diagrams where there is at least one propagator going in between the two Wilson loops, and the disconnected part comes from diagrams where there is no connection between the two Wilson loops, and it factorizes into a product of two Wilson loops. But the thing we're most interested in is the connected part. So at order G squared, the Feynman diagrams for the Wilson loop are of this form, so where we have a single propagator going in between the two loops. And then to get the full answer, we simply sum over the different ways of attaching the Wilson loop, or the propagators between the two Wilson loops. So we can then consider the extension of this correlator to correlation functions of super Wilson loops. And then this correlation function can be expanded into different MHV sectors, as shown here. So K, that K label means that the correlator has Grassmann degree 4K. And we label that we also call that the NK MHV part, borrowing terminology from amplitudes. And it also factorizes into divergent finite and conformally invariant piece. And then the conformally invariant piece can be expanded in MHV sectors, and then each sector can be expanded in loop order as well. So K is the MHV sector and L is the loop order. And N1 to NM are the number of sides on each Wilson loop, each of the N Wilson loops. So we work in twistor space. So each of these Wilson loops depends on the super twister Z, which have 4 bosonic components and 4 fermionic components from the chi's. And yeah, so as we're working in twistor space, Yang-Mills in twistor space is given by, at least perturbatively, is given by holomorphic Chern-Simons theory plus an extra piece, which captures the interactions of the theory. So we have the G squared here for S2. And then the Wilson loop within twistor space is simply defined as the trace of the path ordered product of the sum of this d bar I to the -1 operator on the superfield, and then d bar to the -1 is defined here just in terms of this Green's function, which is given by ds prime over s minus s prime. Then from this theory, from this action, we can get Feynman rules, but another way of getting Feynman rule is by making use of the Wilson loop scattering amplitude duality, which states that the MHV diagrams of scattering amplitudes are in a one-to-one correspondence with the Feynman diagrams of the dual Wilson loop. And this, it's also true that the rule for a propagator within an MHV diagram, so as shown here, this propagator here, is the rule for this is the same as this propagator here within the dual Wilson loop. And it's given by this Orn variant object that James introduced as well earlier. And it's just given by delta 04 of chi a times this 4 bracket BCDE plus cyclic permutations. The delta 04 notation just means that we take the first component of all the chi's within here and then multiply it by the same thing, but with the second components times the third and fourth components. And this 4 bracket is called the twister bracket and is just a determinant of the matrix formed by these 4 twistors. I hat, which appears within the rule, is just given by the intersection of the line I-1I with the plane formed by the reference twistor and J-1J. So if there's no other propagator within in a clockwise direction from this propagator attached to another line, so if this is just the last propagator, then I hat is just replaced by I. That's maybe too technical there. But all in all, we can just use this rule for multiple Wilson loops because this doesn't depend on what lines what Wilson loops the lines are actually part of. So if we consider just an NMHV correlator that has Grassmann degree 4, propagators have Grassmann degree 4, so that means within these diagrams we just have a single propagator. So to get the full expression, we just sum over the different ways of putting a single propagator in between the 2 Wilson loops to get the connected part of the correlator. Then for n squared MHV, that has Grassmann degree 8, so we require 2 propagators and so on. So this is an example of a diagram which contributes to the n squared MHV correlator, where these lines are part of one Wilson loop and this line is part of another Wilson loop. We could also have a diagram where this propagator goes to another Wilson loop and this propagator it goes to another twister line and this propagator goes to another twister line. So just a couple of simple examples. The NMHV part of the connected correlator of 2 Wilson loops is just given by a sum over a single Orn variant, where I runs over the cusps of one Wilson loop and J runs over the cusps of another Wilson loop. Alpha is equal to 1 for SUN, so it vanishes, and for UN it's equal to 0. Then the n squared MHV result is equal to the square of the NMHV correlator, where again I just runs over the cusps of one Wilson loop and J runs over the cusps of another Wilson loop, of the other Wilson loop. So then so that's 3 level correlators, and then we want to move on to doing loop level calculations or order G squared and beyond. So if we take the path integral form of the Wilson loop and then plug in the the Chern-Simons part and the log-det part, and expand in G squared, we get a tree-level part. And at order G squared, we have an integral with respect to the bitwister x of the correlator of a Wilson loop, and this extended operator which lies along the line x. So to compute the loop integrand, we simply need to sum over all ways of attaching propagators between the Wilson loops and this extra line x. So this is an example of a diagram. So again, this is a line on one Wilson loop, and this is a line on another Wilson loop. And this is a contribution to the MHP one loop correlator. So if we use the final nodes again, we get that it's equal to the product of Orn variance. And then we also have fermionic and bosonic integration over the loop twisters. Upon doing the fermionic integration and taking total derivatives and some other algebra, we're able to find that it has a manifestly dual conformally invariant form in terms of dilogs and product of logs, where the Bij's are conformal cross ratios. And any questions so far? Yeah.
Wilson loops in
space. Yeah. So all these diagrams are twistor Wilson loop diagrams. Yeah, in twistor space. So that's why they have like these like go infinitely far in like each direction. But if this is space time, they would just like stop it at the point where we intersect.
the lines in the loop are
the lines, so the twistor lines correspond to points in the cusps of the Wilson loops in space-time. Okay. So now that we have kind of calculational tools for computing tree-level correlators and loop integrands, we now want to find properties and simplifications of Wilson loops. So although we were able to compute the MHV one loop result directly, the loop integration becomes very difficult when we go to higher MHV degree. So we need other routes of calculation to do higher MHV degree. So one way is by expanding the correlator or the amplitude in terms of simple integrals and simple integrands called chiral boxes. And these capture the singularities of the amplitude and correlator. So for an amplitude, which again is equal to a single Wilson loop, there are 5 different chiral boxes. They differ by the number and the distribution of the massless corners. And the cut associated to the poles of each chiral box of the one loop integrand it turn out to give a product of 3 level amplitudes. So this means that the amplitude, anyway, well, so far just the amplitude can be expressed in terms of a sum over very simple integrals with 3 level coefficients. So we can understand how these 3 level coefficients arise by the partitioning of Feynman diagrams which contribute to a given cut. So if we consider the one loop dodecagon at n cubed MHV, and the 4 mass chiral box within the chiral box expansion of that Wilson loop, shown here with propagators 1, 2, 5, 6, 8, 9, and 11, 12. Then for a diagram within the dodecagon to contribute to this cut, to the cut associated to this box, it needs to have propagators going from the Lagrangian line to the line 1, 2, and to the line 5, 6, 8, 9, and 11, 12. So I've drawn the Lagrangian, although we should really draw the Lagrangian line as just a straight line. I've drawn it in a loop to kind of manifest the cyclic symmetry of the Lagrangian line. And then when we do that, we can see that the kind of diagram separates into 4 separate regions. So at n cubed MHV, we need 5 propagators in total. So we have an extra propagator to put into this diagram on top of the four mandatory propagators. We can't have the extra propagator going between 2 different regions because that would be non-planar and it wouldn't contribute in the planar limit. I actually don't think I mentioned all of this is in the planar limit. So that means that the extra propagator needs to stay within a given region. So in this example here, we have a propagator that goes from the line 2,3 to 4,5. And taking that example and using the Feynman rules, it is equal to a product of four Orn variants, which depend on the loop twisters, and then a single Orn variant for the extra propagator. And then if we take the cut of that diagram, those first four propagators go to a product of two propagators, and the fifth one is left unchanged because it does not depend on the loop twisters. And that Orn variant is a diagram within the Wilson loop formed by the twisters within this given region, this sub-region here. And then when we sum over the cuts of the diagrams with the extra propagator within that region, it turns out that that sum gives this product of two Orn variants times the full Wilson loop formed by the twisters within that given region. And then it's a similar story for the other four regions as well, or the other three regions as well. So we get that the coefficient of this four-mass box is given by the sum over four Wilson loops associated to the four different regions within when we include those four mandatory propagators. And then at higher MHV degree, we can see that this is actually a product of the four different Wilson loops. But when we go to n cubed MHV, it reduces to a sum. So I probably need to go a bit quicker, but so then generally the coefficient of the four-mass box is a product consists of two Orn variants times the product of the four different regions. And then for multiple Wilson loops, it's a very similar story, except there are more types of chiral boxes and the regions are slightly more complicated. And yeah, with those extra chiral boxes and the derivation of the tree level coefficients, we have the integrated expression for any one loop correlator. So that's any number of Wilson loops with any number of sides at any MHV degree. So the Q-bar equation, so I'll go through this quickly. The Q-bar equation relates Wilson loops to an integral over Wilson loops with an extra point, so Zn plus 1, so an extra cusp at a higher MHV degree. Then when we expand this expression at recoupling, we get that it relates Q-bar acting on a loop level operator in terms of an integral over lower loop objects. So we get that this Q-bar operator, which is a generator of dual superconformal symmetry, acting on a one loop object gives this simple integral over tree level objects. And this integration is generally much easier than standard loop integration. So it allows us to kind of get higher loop objects. So 2-loop and 3-loop amplitudes have been computed using this. Then we can generalize that Q-bar equation for multiple Wilson loops. And we find that, again, it relates loop level correlators to a sum over tree level correlators, which have a higher MHV degree and a higher extra point on it. And then we want to use that equation to compute 2-loop and 3-loop correlators. And that's what one of the things we're working on at the moment, what Rowan's actively working on as we speak. On Wilson loop. So we also have a BCFW relation for Wilson loop correlators, and essentially this relates correlation functions of Wilson loops to the sum over correlation functions of a smaller number of Wilson loops. Is that not a smaller number? Wilson loops with a smaller number of sides, or a lower MHV degree. And then we use this expression to verify the Q-bar equation. So just to summarize, we developed the calculational tools for Wilson loop Wilson loop correlators at tree level and the loop integrands, and we found various properties of these objects. So they satisfy a BCFW-like recursion relation. They can be expanded in terms of simple integrals called chiral boxes, and the coefficients factorize into tree level correlators. And they satisfy a Q-bar equation, which allows us to get 2-loop and 3-loop objects. So as I said, we are trying to get that 2-loop Wilson loop correlator. We're also trying to find the geometry whose volume gives a Wilson loop correlator similar to the amplitude for amplitudes. And we're trying to understand, trying to get the tree level coefficients for non-planar correlators as well. And then some future things we would like to work on are to reproduce the correlation function of a Wilson loop and Lagrangian by taking a limit of the 2 Wilson loop correlator. And then we like to do some strong coupling calculations and form the OP and look at the spectrum of operators. So thank you very much.
Thank you. Questions for Matthew?
It's too focused.
Yeah.
Or
So you said QR is a generator.
Dual superconformal symmetry, yeah.
So is the QR equation like a Ward identity or?
I think it is. James, you know more on this.
So it's like supersymmetric variation of your loop and inserts a fermion somewhere where you insert. Obtain this fermion, and a way you can obtain it is by edge and taking it's the insertion of a supersymmetry or a biochemical object.
Questions? Right then. Thank you.
Thank you again.